Electromagnetic waves carry finite energy and momentum. Let's account it. The energy per unit volume in electromagnetic fields is given by U equal to UE plus UM, which is the sum of energy stored in the electric and magnetic fields. The energy that is stored in the electric field is given by half epsilon 0 E square, and that stored in the magnetic field is half B square over mu 0. So the sum is half epsilon 0 E square plus 1 over mu 0 B square. In the case of a monochromatic plane wave, we have B square equal to 1 over C square times E square. And when we substitute for C square, that is 1 over square root of mu 0 epsilon 0 the whole square, this equation becomes mu 0 epsilon 0 times E square. Let's substitute this in the expression for the total energy so that U becomes 1 over 2 epsilon 0 E square plus 1 over mu 0 multiplied by mu 0 epsilon 0 E square. The mu zeros cancel. From the two terms, we infer that the contribution of electric and magnetic fields are equal, and the energy is epsilon 0 E square, and this is equal to epsilon 0 E 0 square cos square k z minus omega t plus delta. And this is the energy that is carried by the electromagnetic waves as it travels. We define the energy flux density, that is energy per unit area per unit time, transported by the fields as the Poynting vector. The Poynting vector is defined to be S equal to 1 over mu 0 times E cross B. If the electric field is oriented along the x direction, magnetic field along the y direction, then from this equation we see that the Poynting vector will be oriented along the z hat direction, that is along the direction of propagation. This expression for the Poynting vector is a general one. Let's try to reformulate it in a still more acceptable form. For the monochromatic plane wave that is propagating along the z direction, we take E as E0 cos k z minus omega t plus delta x hat, and B as equal to B0 cos kz minus omega t plus delta along y hat. This is again equal to 1 over c z cross E, and that is equal to modulus of E over c then z cross x hat. We shall write the modulus of E as E. Therefore, this is equal to E over c and then y hat. Therefore, the Poynting vector is 1 over mu 0 E cross B, which is equal to 1 over mu 0 then E x hat cross E over C y hat, and this is equal to E square over mu 0 C then z hat. This is equal to E 0 square cos square kz minus omega t plus delta over mu 0 c along z hat. We shall make a substitution for 1 over mu 0 from the expression for the velocity of light, that is c equal to 1 over square root of mu 0 epsilon 0. Therefore c square is equal to 1 over mu 0 epsilon 0, and then from here we'll get 1 over mu 0 as equal to c square times epsilon 0, and hence the expression for the Poynting vector becomes c epsilon 0 e 0 square cos square kz minus omega t plus delta along z hat. We shall take epsilon 0 e 0 square cos square kz minus omega t plus delta as the energy density U. Therefore, this equation becomes Cu z hat. That is, the Poynting vector is the energy density U times the velocity of waves. Let's try to give this result a physical explanation. We can consider Sun as a source of electromagnetic energy. Near to Sun, the electromagnetic waves are spherical in nature, and as it reaches far away from the Sun, it can be approximated to be plane waves. If we consider the velocity of light as c, then in a time delta t, the distance that is travelled by the electromagnetic waves is c delta t. If we consider an imaginary volume in space having area A and depth c delta t, then the energy that is enclosed in this small volume will be U times A c delta t. When we take the energy per unit time per unit area transported by the wave, it will be equal to UC, which is the magnitude of the Poynting vector. We move on to another important aspect of electromagnetic waves. Electromagnetic fields not only carry energy, but they also carry momentum. The energy that is carried by the electromagnetic waves will be absorbed if the surface is a perfect absorber like a black body, or it will be completely reflected, and in some cases a part of the energy will be absorbed and a part will be reflected. So that is shown schematically in this figure. The momentum carried by the electromagnetic fields gives rise to yet another phenomenon which is known as the radiation pressure. That is, some kind of a force will be felt on the surface on which the electromagnetic fields are incident. We account the momentum density stored in the field as G, which is equal to 1 over c square times the Poynting vector. And for monochromatic plane waves, G is equal to 1 over c square multiplied by Cu z hat, and therefore this is equal to 1 over c u times z hat. So in the discussion we have introduced three new entities: the energy density, which is defined to be U equal to epsilon 0 e 0 square cos square kz minus omega t plus delta; the Poynting vector S, which is 1 over mu 0 e cross b, and which is again equal to Cu z hat; and the momentum density g, which is equal to 1 over c u z hat. And we see that in all these expressions, there is this fluctuating cosine term. So S and G has this fluctuating cosine term through the presence of U. In the case of light, the wavelength is very short, approximately of the order of 5 power 10 raised to minus 7 meter. When we calculate the corresponding period, that will also be very small and approximately of the order of 10 raised to minus 15 seconds. So that when we make any macroscopic measurement, it will encompass many cycles. That is, the fluctuating cosine squared term appear in the energy and momentum densities. We can get rid of this fluctuating cosine term by introducing its average value. The average value of the cosine squared term over a complete cycle can be shown to be equal to half. The average value of the cosine square term over a complete cycle, that is from 0 to t, is defined to be integral 0 to t cos square theta d theta over t. And this is equal to integral 0 to 2 pi cos square theta d theta over 2 pi. This is equal to 1 over 2 pi integral 0 to 2 pi. The cos square term can be written as 1 plus cos 2 theta over 2 d theta. From the trigonometric relation, cos 2 theta equal to 2 cos square theta minus 1. And this is equal to 1 over 4 pi theta plus sine 2 theta divided by 2. The integration limits are from 0 to 2 pi. And this is equal to 1 over 4 pi multiplied by 2 pi plus sine 4 pi. When we apply the integration limits, the second term is 0, so that we will get the final result as equal to 1 over 2. Therefore, we can write the average value of the energy density, which we represent as U inside angular braces, and this is equal to epsilon 0 E0 square cos square kz minus omega t plus delta, and this is equal to epsilon 0 E0 square cos square kz minus omega t plus delta, and that is equal to 1 over 2 epsilon 0 E0 square. The average value of the Poynting vector is 1 over 2 c epsilon 0 E0 square along the z hat direction, and the momentum density is 1 over 2c epsilon 0 E0 square z hat. The average power per unit area transported by an electromagnetic wave is called its intensity, and it is defined to be the average value of the Poynting vector. This is 1 over 2 c epsilon 0 E0 square. When light falls at normal incidence on a material, depending upon the type of material, it delivers momentum to the surface. If it is a perfect absorber, it will accept all the energy that is incident on it. If it is a perfect reflector, it reflects all the energy that is incident on it. And in most of the cases, a part of the energy will be absorbed and a part will be reflected back. In a time delta t, the momentum that is transferred to the surface can be written as delta p. This is equal to the average value of g multiplied by a, then c delta t. We define the radiation pressure, which is the average force per unit area, as P equal to force per area, and this is equal to delta P over delta T, that is the rate of change of momentum, over A, and this is equal to average value of G multiplied by A C delta T over A delta T. A's and delta T's get cancelled, resulting in 1 over 2 epsilon 0 E0 square. And in terms of the intensity, this can be written as I over C. So this equation gives the radiation pressure that is felt on a black body, that is a perfect absorber. If the surface is a reflecting one, then the waves that are incident on the surface will be specularly reflected. Because of the recoil due to the reflected wave, the surface will further feel a contribution to the radiation pressure. In the case of a perfect reflector, this recoil pressure will be identical to the pressure caused by the incident wave, and hence the net pressure on reflecting surfaces will be twice as the incident one. Let's see how to account this pressure qualitatively. We know that material objects consist of charged particles. The electric field in the electromagnetic waves drives the charges along the x direction. And then the magnetic field exerts a force Q equal to V cross B in the z direction. And the net all the charges in the surface produces the radiation pressure. Let's now do this problem. The intensity of sunlight hitting the earth is about 1300 watts per meter square. If sunlight strikes a perfect absorber, what pressure does it exert? How about a perfect reflector? What fraction of atmospheric pressure does this amount to? We know that the radiation pressure is I over C, where I is the intensity of the light and C is the velocity of light. Therefore, the radiation pressure is 1300 watts per meter square divided by 3, then power 10 raised to 8. When we calculate, the value turns out to be 4.3 to the power 10 raised to minus 6 Newton per meter square. We shall now proceed to do the second part. For a perfect reflector, due to the recoil effect, the pressure is twice as great as the incident one. Therefore, the net pressure is 2 times the incident pressure, and this is equal to 2 times 4.3 to the power of 10 raised to minus 6, and this is equal to 8.6 to the power of 10 raised to minus 6 Newton per meter square. Now the third part. The atmospheric pressure is 1.03 to the power of 10 raised to 5 Newton per meter square. So the pressure of light on a reflector is 8.86 to the power of 10 raised to minus 6 divided by 1.03 to the power of 10 raised to 5. And this is equal to 8.3 to the power of 10 raised to minus 11 atmospheres. The occurrence of radiation pressure can be felt in many physical phenomena. It has tremendous importance in astrophysics as many of the observed astronomical phenomena, including the comet appearance, are explained by radiation pressure. The comets are pieces of ice material that contain frozen gases as well as rock and dust particles. When a comet gets close to the sun, it warms up and begins to evaporate. The coma is a hazy area in the comet which is caused by gases and dust. And the gases and dust that escape from the comet form tails. As indicated in this figure, a comet has two tails. Ionized gases dominate the ion tail or gas tail. These ions interact with the solar wind, which is a continuous stream of charged particles released by the sun electromagnetically. The solar wind exerts such a tremendous force on the ionized gases that the ion tail almost invariably points directly away from the sun. The dust particles make up the second tail. The dust tail does not interact with the solar wind because it is electrically neutral. This tail, however, is influenced by the radiation pressure produced by the sun's light. Although this pressure is quite small, it is strong enough to cause the dust tail to be displaced from the path of the comet, as shown in this figure. This web page by LibreText can be referred to have still more idea on the occurrence of radiation pressure.